Hello everyone, welcome back to part 2 of this tutorial. In this part, we'll present how to use Lyapunov drift method to derive finite sample bounds of reinforcement learning algorithms. So reinforcement learning has seen remarkable successes in solving many practical problems, such as the famous AlphaGo and the recent DeepMind street-learn navigation project. The reinforcement learning problem is usually modeled as a Markov decision process. In this part, we'll consider an MDP defined by a finite set of states, a finite set of actions, a transition probability matrices that are indexed by actions, a reward function, and a discount factor gamma, which is between 0 and 1. So the dynamics of Markov decision process is presented in the following. So at each time step k, the agent chooses some action ak, and the system dynamics then return the agent a reward rk and drives the agent to a new state sk plus 1. And this process is then repeated. In order for a Markov decision process to progress, we must specify a rule of choosing actions based on the state of the environment. This is called a policy, and it's mathematically defined to be a mapping from the state space to probability distributions supported on the action space. For a given policy pi, its performance is measured by its value function, v pi. The value function v pi at state S is defined to be the total discounted reward, starting from state S and then following the policy pi thereafter. Similarly, we can define state action value function Q of a policy pi at state action pair S, A to be the total discounted reward starting from state S, first taking action A, and then follow the policy pi thereafter. With the value function being defined above, the ultimate goal of reinforcement learning is to find an optimal policy pi star in the sense that its corresponding value function is maximized. This is called the control problem, and one way to solve it is the Q-learning algorithm, which we will study later. In reinforcement learning, an intermediate goal is to find the value function of a given policy pi. This is called the prediction problem, or the policy evaluation problem. This intermediate goal of policy evaluation is very important in many reinforcement learning algorithms, such as the approximate policy iteration or in the actor critique framework. There's one thing to emphasize that the reinforcement learning problem is essentially an MDP, but the underlying transition probabilities and the reward function are unknown to the agent. A key feature in reinforcement learning is the Bellman equation. So the Bellman equation for the value function v of a policy pi is presented in the following. So on the left-hand side, we have the total discounted reward starting from state S. On the right-hand side is a combination of one-step reward plus discounted future reward, and they are equal. This is called the Bellman equation. It turns out that the value function v pi uniquely solves this equation. Therefore, to solve the policy evaluation problem, it's enough to solve this Bellman equation. The right-hand side of the Bellman equation can be compactly written as an operator t pi acting on the value function v pi. By the way, the operator t pi is called the Bellman operator. So this Bellman equation is a fixed point equation for the Bellman operator t pi, and v pi is a unique fixed point. Similarly, for the Q function, the state action value function associated with the optimal policy, which we call Q star, uniquely solves its Bellman equation. Here, the operator T is called the Bellman optimality operator. So finding the optimal Q function Q star is closely related to finding an optimal policy. So in this case, finding an optimal policy reduced to finding Q star, which can be found by solving this Bellman equation here. So both the policy evaluation problem and the control problem eventually reduce to solving a fixed point equation of the form h bar of x equal to x, where this h bar is an operator and it's unknown, because in both the Bellman equation for V and the Bellman equation for Q, it has the expectation with respect to the underlying transition probabilities of the Markov decision process, which is unknown to the agent in reinforcement learning setting. We will first present the TD learning method for solving the policy evaluation problem. So the goal here is to estimate the value function v pi of a given policy pi. We next present the TD learning method with synchronous update. I will explain later what synchronous means. So TD learning method is an iterative algorithm. We first initialize v0 arbitrarily. Then, for each k greater or equal than 0, in each time step, for each state S, we sample an action based on the target policy we want to evaluate, and then sample a transition from the underlying system dynamics. Then the corresponding entry of the vector valued iterate vk is updated according to the formula here. We see that the amount of updates, which is after the step size alpha k, is exactly the difference between the left-hand side and the right-hand side of the Bellman equation. But since we don't know the expectation is replaced by sample estimate, and this is called temporal difference. Since in each iteration, we need to sample a transition from every state and update the corresponding entry of the vector valued iterate. This algorithm is called synchronous TD learning. Synchronous TD learning is usually not used in practice because it's usually untractable to generate a transition for each state in every iteration. But we will study this algorithm to see that the L2 norm contraction stochastic approximation result we studied in part 1 can be directly used to establish finite sample bound of TD learning with synchronous update. In order to do that, we first reformulate the TD learning algorithm as a stochastic approximation algorithm. It turns out that we can equivalently write the TD learning algorithm in this in the following way here. So it's a vector update, and the amount of update here is exactly the difference between the left-hand side and the right-hand side of the Bellman equation, which is t pi vk minus vk, plus some noise wk. This noise arises because in the update equation, we replace the expectation by sample estimate, which introduce noise. Okay, now we have the update equation for synchronous TD learning. We next establish the properties of the Bellman operator t pi and the noise wk, which essentially enable us to apply the stochastic approximation results we studied in part 1 of this tutorial. Under some mild conditions, it was shown that the Bellman operator t pi is a contraction mapping with respect to some weighted L2 norm with suitable weights. And the contraction factor is the discount factor gamma, which is between 0 and 1. And also, the noise sequence is a martingale difference, which means it's conditionally mean 0. And its conditional variance is bounded affinely by the current iterate. These two properties enable us to apply the weighted L2 norm contraction stochastic approximation result in part 1. But we will not state the result here. Instead, we will consider a more general version of TD learning, which is n-step TD with asynchronous update, and we will state that general result later. Next, we consider the Q-learning algorithm. So the Q-learning algorithm is designed to estimate the optimal Q function Q star. After that, we can just do argmax to get an optimal policy. In order to estimate Q star, we will consider the Q-learning algorithm with asynchronous update. I will explain later what asynchronous means. So the first step is sample collection. We choose a suitable behavior policy, which we call pi b, and apply it on the underlying system dynamics to obtain a sequence of samples, a sequence of state action pairs. And then based on that, we update the estimate qk of q star in asynchronous manner based on the equation here. So in each iterate, look at all the state action pairs. Let's focus on the state action pair that's encountered in the case step by the sample trajectory. And we only update that the Q function at that state action pair. And the update formula is here, which is similar to TD learning as the amount of update is the difference between the left-hand side and the right-hand side of the Bellman equation for Q function, where the expectation is replaced by sample estimate. Since we only update one component of the vector valued iterate in one iteration, this algorithm is called asynchronous Q-learning. So to study this algorithm, we will first reformulate it as a stochastic approximation algorithm. With a suitable defined operator h, we can write the Q-learning algorithm in a vector form here. So the amount of update is h of qk yk minus qk, where this yk is defined to be the triple sk ak xk plus 1, and is a Markov chain. We will make the following assumption to study the Q-learning algorithm. So we will assume that the Markov chain yk is irreducible and aperiodic. This would imply that this Markov chain has a unique stationary distribution, which we call kappa, and also mixes at a geometric rate. An important property of Q-learning is that the expected operator h bar is a contraction mapping with respect to the L infinity norm, where this h bar is defined to be the expectation of the noisy operator, where the noise yk is sampled from the stationary distribution. This is a notable difference from the stochastic approximation algorithm we studied in part 1, where it's a contraction mapping with respect to an inner product norm. Here, sup norm is not an inner product norm, and it will introduce additional challenges. Using the expected operator h bar, we can rewrite the update equation of Q-learning in the following form. What I did here is simply adding and subtract h bar of qk. So there are two terms I highlighted here. The first term is h bar of qk, where this h bar is a sup norm contraction. And the red term here is the difference between the noisy operator and the expected operator. Since we have a Markov chain here, this represents the Markovian noise. The Markovian noise can be handled by using a conditioning argument. The main challenge here is how to handle L infinity norm contraction. In fact, it is mentioned in the classical textbook, Neurodynamic Programming, that unfortunately, it is unclear whether one can define a smooth potential function, in this case, a Lyapunov function, M, such that the update of the Q-learning is along the descent direction with respect to the Lyapunov function. In this tutorial, we will show how to construct a smooth Lyapunov function to study the Q-learning algorithm, hence resolving this issue. Since we have modeled Q-learning algorithm as a Markovian stochastic approximation, we will go ahead and study a general Markovian stochastic approximation algorithm under arbitrary norm contraction assumption, which include sup norm contraction as a special case. The algorithm we are going to study here is of this form. Xk plus 1 equal to xk plus step size times h of xk yk, where yk is some noise, minus xk plus wk, and wk here is another additive noise. It turns out that both Q-learning and synchronous TD learning we studied earlier can be formulated in this form. And beyond that, other algorithms such as n-step TD, TD lambda, off-policy TD learning algorithms such as V-trace and Q-trace can all be modeled in this form. So this stochastic approximation algorithm enables us to study value-based reinforcement learning algorithms in a uniform manner. We will next state our assumptions. The first assumption is that the noisy operator H is globally Lipschitz continuous with respect to X. The second assumption is that the Markov chain YK is irreducible and aperiodic. This implies that it has a unique station distribution and also mixes at a geometric rate. The third assumption, which is the most important one, is that the expected operator H bar is a contraction mapping with respect to some arbitrary norms, call it C norm, where this C stands for contraction, with contraction factor beta between 0 and 1. This C norm can be arbitrary. It can be a weighted L2 norm we studied in part 1. It can also be the sup norm we study in Q-learning. The last assumption is that the additive noise WK is a martingale difference whose conditional variance is bounded affinely by the current iterate. Next, we will first state our result for finite sample guarantees of this stochastic approximation algorithm, and then we will provide the proof sketch. We will first consider using constant step size in this stochastic approximation algorithm. And we have the following finite sample bound. When the constant step size is properly chosen, we have this following inequality here. So this is analogous to the finite sample bound we studied in part 1. One difference is that in the second term of this bound, which represent the impact of the variance, we have an additional log 1 over alpha term, as opposed to only alpha in part 1 of this tutorial. This additional log factor is because of the Markovian noise. Since Markovian noise is not conditionally unbiased, we have this additional term on the second term here. Another thing I want to mention is that the constant C1, C2, C3 are not numerical constants. They depend on the contraction norm. If the contraction norm is weighted L2 norm, we have a set of constant here. And if it's sup norm, we have a different set of constant. So we will see more explicitly what the constants are when we study the Q-learning algorithm later. We next present the result for using diminishing step size of the form alpha divided by k to the power psi, where psi is some constant between 0 and 1. If we use this step size, we have the following finite sample bound here. So this bound is analogous to the bound we learned earlier in part 1. So when psi is between 0 and 1, the convergence rate is roughly 1 over k to the power psi. But when psi is equal to 1, the convergence rate crucially depends on the constant alpha. Specifically, when alpha is very small, the convergence rate can be arbitrarily bad. The optimal convergence rate of log k over k is achieved only when alpha is above some threshold. One difference between this result and the result in part 1 is that we have an additional log k factor in the bound. This log k factor is similar to the constant step size setting, and it's because of the Markovian noise we have in this stochastic approximation algorithm. We will next provide the proof sketch of these results. For simplicity, we will only provide the proof for L infinity norm contraction, which is the case for Q-learning. So let's first identify the corresponding ordinary differential equation. So we write the stochastic approximation algorithm in this form, where we send xk to the left and then divide both sides by the step size. Now, if we let step size go to 0 and ignore all the noise term, we get the following ordinary differential equation, where the left-hand side is by letting alpha go to 0, and the right-hand side is by ignoring yk and wk. So the connection between stochastic approximation and ODE are very close. So in particular, we can show that if the ODE is globally asymptotically stable, then under some mild assumptions, the stochastic approximation algorithm converge to X star almost surely. In order to study the finite sample bound, to get intuition, we first see what's the Lyapunov function we use to study the ODE. It turns out that we can directly use the sup norm square to serve as a Lyapunov function. This is because the operator h bar is a contraction with respect to sup norm. By using the sup norm square as a Lyapunov function, we can derive this one-step drift inequality, which says that the derivative of the Lyapunov function is less or equal than some minus number times the Lyapunov function. And by integrating this one-step drift inequality, we get the exponential convergence rate of the ODE. We need to pay attention at the term, the blue term in the middle of the one-step drift inequality. It's the dot product between the gradient of the Lyapunov function and h bar of x minus x. And this term will also appear when we study the stochastic approximation algorithm. Now we have the Lyapunov function for the ODE. We need to construct a Lyapunov function for the stochastic approximation algorithm. The stochastic approximation algorithm is different from ODE because of two reasons. First is that we don't have continuous updates, we have discretized updates. That's why we have a discretization error. By adding and subtract h bar of x on the right-hand side of the update equation, we see that we can decompose the update into three terms. The first term, the blue term here, is h bar of x minus x, which coincides with the right-hand side of the ODE, and we call it the ODE term. This term will eventually provide us a negative drift. The second term and the third term represent the impact of the Markovian noise and the martingale difference noise, which we will have to control them. When we study the ODE, an important step is to derive a one-step drift inequality. Similarly, for stochastic approximation algorithm, we also need to derive a one-step drift inequality. Well, what should we expect of that one-step drift inequality? So we need to find a Lyapunov function m, and then the one-step drift inequality we wish for is of this form. So let's compare it with the one-step inequality of ODE. On the left-hand side, the ODE has derivative. In stochastic approximation, we have the difference. On the right-hand side, the ODE has negative drift. We also have negative drift in stochastic approximation, which is the minus big O1 term. But because of the discretization error and the stochastic error, we also have two terms, the two error terms that are captured by the two small O1 term. Once we have the ODE one-step drift inequality, we can directly integrate it to get convergence rate. Similarly, once we have the stochastic approximation one-step drift inequality, we can repeatedly use it to get a finite sample bound on the iterate. So all we need to do is to construct a valid Lyapunov function m, such that the one-step drift inequality holds. So what kind of Lyapunov function can give us this one-step drift inequality? What kind of properties should this Lyapunov function have? Well, the first property we need is smoothness. Why is that? First of all, recall that in part 1 of this tutorial, where convergence bound of weighted L2 norm contraction stochastic approximation algorithm was derived. A very important property used there is the binomial theorem for the weighted L2 norm. Here, this smoothness property can be viewed as an extension of the binomial theorem. To see this, suppose my Lyapunov function is just a weighted 2 norm square, and this infinity norm here is 2 norm. Then this equation is exactly the binomial theorem. Now, since we have arbitrary norm, we don't have a binomial theorem. We have this smoothness property. One can also view this. One can also understand the smoothness property in this way. The difference between my and mx can be represented using Taylor series. The smoothness property says that we can ignore all the higher order terms of the Taylor series and upper bound it by some constant times the second order term. This enables us to control the discretization error in stochastic approximation. Note that the sup norm square is not a smooth function. Therefore, we cannot directly use the ODE Lyapunov function as the stochastic approximation Lyapunov function here. The second property we need is the approximation property. It states that the Lyapunov function should be a good approximation to the sup norm square. There are two reasons for that. One is that since m is some abstract function, eventually we don't want to state the finite sample bound in terms of n. We want to state it in terms of sup norm square. Therefore, we need an inequality to translate m into sup norm. The second reason, which is more important, is that the expected operator h bar is a contraction mapping with respect to sup norm. In order to exploit this property, we somehow need the Lyapunov function to be close to sup norm square. So in order to construct a smooth approximation of the sup norm square, what we do here is use the so-called generalized Moreau envelope. The generalized Moreau envelope is defined to be the minimum of these two functions, and it is called the infinimo convolution. The infinimo convolution is sort of like the convolution, but instead of having product, we have summation here. If the p norm here is 2 norm, the Euclidean norm, then this is the standard Moreau envelope. Here we extend this definition to the case where we can use some arbitrary smooth norm here. In this case, we call it generalized Moreau envelope. This p norm and the parameter theta are all tunable parameters, and eventually we will have to carefully choose them to obtain the tightest finite sample bound. An important property of this Moreau envelope is that itself is also a norm square function. Although we cannot explicitly compute the Moreau envelope, we can show that all requirements for being a norm is satisfied. Now let's show that this Moreau envelope has the required smoothness property and the approximation property. And the first one is that the Moreau envelope is p minus 1 over theta smooth function with respect to p norm. This is from a standard optimization result. In fact, if we use any smooth norm here, the Moreau envelope itself will be a smooth function. The second property is the approximation property. We see that the Moreau envelope can be bounded above and below by some constants, in this case a and b, times 1/2 sup norm square. So this theta appears, this parameter theta appears in both the smoothness property and the approximation property. In fact, this theta trades off the smoothness and approximation. To see this, if we choose a very small theta, then in this case, both the constants a and b are close to unity, and we have a very good approximation. But since theta is small, this smoothness parameter is very large. Therefore, we don't have a very smooth function. This makes intuitive sense because since we want to find a smooth approximation of sup norm square, which is not a smooth function, if we want a good approximation property, then the function cannot be very smooth. If we want it to be very smooth, it cannot be a very good approximation to the sup norm square. So eventually, we need to tune the parameter theta to get our tightest finite sample bound. Now that we have constructed the Lyapunov function, we will use it to study the stochastic approximation algorithm. So let's first write the update equation of the stochastic approximation algorithm here. What I did is I sent xk to the left, and for the amount of updates, I add and subtract h bar to form these three terms we have seen earlier. The first term is the ODE term, and the second and third term are Markovian noise and martingale difference noise. So to use the Lyapunov function, we start with the definition of smoothness. This first inequality is just the definition of smoothness. We apply it on the difference between xk plus 1 and xk. And the next step is to substitute the update equation of xk plus 1 minus xk into the right-hand side of this inequality. And we obtain the four terms here. The first three terms correspond to the three terms on the right-hand side of the update equation. And they have the expected updates. They are due to Markovian noise, and they are due to martingale difference noise. And the last term is just the discretization error, and it's just the norm square of the right-hand side of the update equation. Now, let's first focus on the expected update, which is the blue term. Recall that this is exactly the term that appears in the middle of the ODE one-step drift inequality. Hence, this term will give us a negative drift, which is of order step size alpha k. For the error terms, let's first consider the simplest one, which is the martingale difference noise. So in the martingale difference noise, we can use the definition of martingale difference to see that by using conditional expectation and tower property, this term is exactly 0. Then let's look at the discretization error. So this term is easy to handle because it's of the order alpha k squared, while this negative drift term is of the order alpha k. So when the step size is small enough, this error due to discretization can be dominated by the negative drift. The most challenging term here is the error due to Markovian noise. So to handle this, we need to use a conditioning argument. The high-level idea is the following. Let's consider the second term in the inner product here. So it's h of xk yk minus h bar of xk. Suppose we take conditional expectation conditioning on a mixing time ago. Then, since the Markov chain mixes geometrically fast, the conditional expectation will be very close to the expectation with respect to the stationary distribution. Therefore, the difference between these two terms are very small, and hence the whole term is small, which enable us to control it. After we control all these terms, we arrive at the one-step drift inequality. So the expected update will contribute to the negative drift minus big O of alpha k term here. And the error due to Markovian noise, martingale difference noise, and discretization error are all captured in the two small O of alpha k term. So this inequality is exactly the one-step drift inequality we desire. And by iteratively using this inequality, we get finite sample bound we presented earlier. The key step in this proof is the construction of the Lyapunov function using generalized Moreau envelope. Now we have presented the stochastic approximation result for arbitrary norm contraction. We use it to study the Q-learning algorithm. Recall the Q-learning update equation. So in each iteration, for the state action pair that is visited by the Markov chain, it's updated according to the formula here. So we said that Q-learning can be modeled as a Markovian stochastic approximation algorithm. So this is the formulation, and we have the H operator here. And YK is a random process, which is a Markov chain, and it's defined to be the triple SK, AK, XK plus 1. We have seen all of this earlier. So in order to apply our result, we need to show that all the assumptions are satisfied. We here only show the one assumption, which is the subnorm contraction property. So define the expected operator to be the expectation of the noisy operator, where the random variable y is sampled from the stationary distribution. In this case, we can explicitly compute the expected operator, which is given by this formula here, k times tq plus I minus k times q, where t is the Bellman operator for the q function, and k is a diagonal matrix, where the diagonal entries are the stationary probabilities of visiting state action pairs. So if we focus on one particular state action pair, then h bar q of SA can be viewed as a convex combination of the Bellman operator and the identity operator, where the weights are the stationary probabilities. This captures the fact that in Q-learning, one specific entry state action pair is updated with probability P of SA asymptotically, and with probability 1 minus P of SA, it remains unchanged. Similarly, we can show that the expected operator H bar is a contraction mapping with respect to subnorm, with contraction factor being 1 minus k min times 1 minus gamma, where k min is the minimum entry of the stationary distribution on state action pairs. And also H bar has a unique fixed point Q star. So all the assumptions of applying our stochastic approximation results are satisfied. We next present the finite sample bound of asynchronous Q-learning algorithm. Here is our result. For simplicity, here we only provide the result for using constant step size. So when the step size is properly chosen, we have the inequality here. The right-hand side is composed by two terms. The first term goes to zero geometrically fast, and the second term is a constant which is proportional to step size times log 1 over step size. From this finite sample bound, we can derive the sample complexity. So in order to achieve epsilon accuracy, our sample complexity scales of this form. So the first term here is order 1 over epsilon square. It captures the dependency on the accuracy. The second term is 1 over 1 minus gamma to the power 5. This captures the dependency on the effective horizon, which is defined to be 1 over 1 minus gamma. And the third term here is the minimum entry of the stationary distribution raised to the power minus 3. And this captures the quality of exploration. So in the best case, where k-mean is 1 over SA. In this case, our bound scales as state action, the size of state action space raised to the power 3. So this is the state-of-art mean square bound in the literature, and it is also comparable to the state-of-art concentration bound in Lyapunov 2020. Beyond Q-learning, our result can be used to study multi-step TD learning. Recall that we studied synchronous one-step TD learning in the very beginning. Here, we generalized that result to use multi-step bootstrapping and asynchronous updates. So we first present the n-step temporal difference learning algorithm. So the goal is to estimate the value function v pi of a target policy pi. So the first step is to collect a sequence of state action pairs under the target policy pi. And based on these samples, we update the estimate vk in an asynchronous manner according to the formula here. So similar to Q-learning, the entry of vk is updated only when it coincides with the state visited at time k. And the amount of update, instead of using one-step return, we're using n-step return here. This is a major difference between n-step TD and one-step TD. And another difference, of course, is that we're using asynchronous update. In n-step TD, there is always a question about how to tune the parameter n to improve the performance of the algorithm. Here I present a graph from the classical textbook Sutton and Bartle 2018. We see that this is the root mean square error as a function of the step size and the choice of n. So to see the impact of n, let's fix a step size. For example, let's look at when step size is equal to 0.4. In this case, n equal to 4 has the best performance. And then it's probably n equal to 2, and then n equal to 8, and then n equal to 1. So we see that usually large n does not give the best performance, small n does not give the best performance, and the intermediate value of n usually gives the best performance. But can we prove something about it? Can we theoretically say that for some choice of n that gives the best performance of the algorithm? Well, since n-step TD can be modeled as a stochastic approximation algorithm we studied before, we can derive finite sample convergence bound of n-step TD. And the bound will be an explicit function of the parameter n. And by optimizing the bound in terms of n, we get an optimal choice of n. This is what we're going to do next. Because of time limit, I'm not going to show the finite sample bound here, but I'm going to show the sample complexity bound, which is an implication of the finite sample bound. So the sample complexity bound of n-step TD is presented here. Similarly to Q-learning, we have the dependency on the accuracy, which is epsilon minus 2. And there is a dependency on the effective horizon, which is 1 over 1 minus gamma to the power 2. And the last term captures the quality of exploration. But here we'll only focus on the term that's dependent on n, which is the third term, and it's marked in blue. So now we can clearly see a trade-off. So n appears linearly in the numerator, which means that we cannot choose n too large because it increases linearly. But also we cannot choose n to be too small. If n is very small, then the denominator becomes very small. In this case, the whole thing also becomes large. So by optimizing this term in terms of n, we get a roughly estimate of the optimal choice, which is 1 over log 1 over gamma. So this makes intuitive sense because when the discount factor is very small, it doesn't make sense to use n-step TD. But when the discount factor is large, close to 1, then in that case, using n-step TD has provable better performance according to our result here. So this is the first known result in the literature. Other than n-step TD, our result can be used to study the TD lambda algorithm. The TD lambda algorithm is a family of TD learning algorithm parameterized by the parameter lambda. So similarly, there is a question of efficiency of bootstrapping here. If lambda is small, it's more bootstrapping. If lambda is close to 1, it's more Monte Carlo. The question is about how to choose the parameter lambda to get the best performance of the algorithm. Similarly, using our result, we can derive finite sample bound and sample complexity. Based on the sample complexity, it provides our insight about how to tune the parameter of lambda to improve the efficiency of the algorithm. Other than the TD lambda algorithm and n-step TD learning algorithm, which use on-policy sampling, our result can be used to study off-policy multi-step TD learning algorithm, such as V-trace and Q-trace. So in off-policy TD learning, one usually uses important sampling ratios to correct the difference between the target policy and the behavior policy. So by deriving sample complexity and finite sample bound, our results provide insight about the bias variance trade-off for using truncated important sampling ratios for different truncation levels. So we've discussed about how our result can be used to derive convergence bounds of TD learning algorithms. So the TD learning algorithms are used to solve the policy evaluation problem in reinforcement learning, and it's usually an intermediate step in the actor critique framework. So by establishing finite sample bound of the critique, we can use it to provide the total finite sample bound for the actor critique algorithm. So for example, since our result can be used to study off-policy TD, we can use off-policy sampling in the critique in the natural actor critique framework. So this enables us to, on the one hand, ensure exploration, and on the other hand, avoid using on-policy sampling where one needs strong assumptions to ensure exploration and get theoretical performance bound. So by using off-policy sampling in the critique, in the tabular setting, we show that natural actor critique plus Q-trace gives us epsilon minus 3 sample complexity. This is the state-of-art result in the literature. In the function approximation setting, we show that natural actor critique with n-step off-policy TD learning with linear function approximation gives epsilon minus 3 sample complexity too. This is also state-of-art result in the literature. Okay, let's summarize the tutorial of this part of the tutorial. So in this part, the key idea is the construction of Lyapunov function in the case of arbitrary norm contraction. So the first step is to identify the ODE and use the ODE to identify the Lyapunov function. In this case, we get 1/2 norm square. But 1/2 norm square may not be a smooth function for us to study the stochastic approximation algorithm. What we actually need is a smooth approximation of the norm square. To do that, we use the generalized Moreau envelope, which gives us a smooth approximation, and also the tunable parameters enable us to get the tightest possible finite sample bound. The smoothness property is kind of an analogy of the binomial theorem in the talk of part 1, and it enables us to control the discretization error and the noise error. This is the end of part 2. Thank you for listening, and now is the time for questions.